So for this unit, what we're going to be focused on is the life cycle of a star. And what this unit is picking up on is the concept we learned about from the Big Bang. And after the Big Bang, all of the energy, all the matter necessary for everything that's in our universe was created in an instant. And stars are formed from remnants of the Big Bang, formed in what are known as nebulas, which are huge clouds of gas and dust that eventually, through gravity as they spin together, result in the actual formation of a star. So if we look at this slide, what we're looking at is two different ways in which a star can basically live out its life. So all stars begin in the same way, in what are known as nebulas, or in this case a stellar nebula. And that's the very first slide all the way to the left. And what these stellar nebulas are is these huge groups of gas and dust that eventually, through the force of gravity, start to spin together. So stars go one or two ways. So if you look at the top, you can see the portion of a star. It's similar to how ours is. It creates a medium or small sized star. And this is the main sequence of its life, basically when it's produced or it's burning through hydrogen and nuclear fusion is occurring in the middle, giving off tons of energy in terms of heat and light. What happens after that is stars, just like any other organism in our solar system, or at least on Earth, they'll die. And so what you get is you get to this red giant stage. And this red giant stage, a star is starting to burn through most of its hydrogen. It's actually starting to burn helium. And the star actually starts to extend out. And this is actually how Earth will one day be destroyed, is that the star itself will become a red giant. It'll start to expand outward into our solar system and actually absorb all of the material in its way. Once this has happened, you get what's called planetary nebula. Basically, that's this really, really vast cloud. Very little energy is still left in the star. Then goes to a white dwarf. These are really, really small stars that burn not very bright, and they give off very little energy. And eventually, it results in a black dwarf. This is the death of a star, where the star itself is actually lost its energy. The other way has to do with the way large stars go through their life cycle. So if you look at the bottom options, you have a massive star. Think about the blue star that we saw at the launch video. These will then go into these red supergiants, which, just like a normal red giant, they start to expand outward. They just do so much larger. Eventually, these red supergiants result in what's known as a supernova. This is an explosion of the star's energy. This energy can eventually actually be used to create new stars or planets or moons. And after a supernova, one or two things happen. Either we get the formation of what's known as a neutron star, and these are really small, fast spinning stars that give off radioactive radio waves known as pulsars, or they become what's known as a black hole. And these black holes are basically when a star collapses in on itself and it starts to spin and absorb everything that's around it. So the beginning of a star, what you get is formed from this planetary nebula. It has to do with the star's mass. The more mass there is, the bigger the star forms. The bigger the mass, though, the bigger the star, the more energy it burns, the faster it burns, the shorter its lifestyle. It basically runs through its energy really, really fast because there's a ton of it. Really, really fast in terms of being millions of years, of course. So the more matter, the more dust, the more gas in these nebula clouds that there are, the bigger the stars will actually form. So if we look at this picture right here, this is the Crab Nebula, and nebulas are actually named after objects that they look like. So in this case, scientists decided this looked like a crab. If you look at the front, maybe you see the crab's face and two little pinchers down below. But so this is taken from the Hubble telescope, and as you can see in the middle, really, really bright blue light. And this is actually where the stars themselves are starting to form. You can see the gas and the dust clouds. The outer portions are a little bit lighter. There's a little bit less energy out there. But eventually, everything's going to get pulled towards the center of it. And as it gets pulled towards the center, it starts to spin, and it gets hotter and hotter and hotter during nuclear fusion. And what this is this is the concept of hydrogen atoms just bouncing off each other faster and faster and faster, creating heat and light. So nebulas themselves, nebulas are vast clouds of dust and gas. And these nebulas are millions, if not billions, of miles long and wide and go in every direction. And what happens is over time, these nebulas start to kind of pull in on themselves. So these dust clouds, these gas clouds, start to get pulled together by gravity. And as gravity pulls things together, it makes it tighter and tighter and tighter. It squeezes it together. And as it squeezes it together, it actually starts to rotate. And as it starts to rotate, these hydrogen atoms start to bounce off each other faster and faster and faster. And this is what's called nuclear fusion. This bouncing of these atoms off of each other, this nuclear fusion, results in massive increases of temperature to millions of degrees. And as these temperature increases, it goes faster and it starts to spin faster and faster and faster. And as it spins faster, it gets hotter, and it's a trend. So it gets hotter, it spins faster, it gets hotter. And eventually it spins fast enough that a star is actually born, which is just a massive let off of energy all at once. So as you can see in this slide, what we're talking about is the spinning of the cloud, these hydrogen atoms colliding together, resulting in a massive temperature increase. This is nuclear fusion. And as the temperature rises, the atoms of hydrogen bounce off of each other. And the faster they bounce, the more heat they create. The more heat they create, the more light that's given off. And as these changes happen, the nebula itself actually begins to break apart. And once the nebula breaks apart, what you get is what is known as a protostar. And this is actually a baby star. This is the very beginning of a star's life. So if you look at this slide right here, what you're actually seeing is you're seeing a relationship between the amount of mass in a star formation in terms of its nebula and how the actual star itself is formed. So if you start from the bottom and work your way towards the top, you see we always start with a protostar. But towards the bottom, these are very small nebulas, meaning they have very little energy. You can see it creates what's known as a brown dwarf, stars that give off very little energy. If you look at the next one up, it's called a red dwarf. Once again, it gives off very little energy, and it continues as a red dwarf for most of its life, eventually becoming a white dwarf. The third one from the bottom, this is actually based on our solar system. You can see this is similar to what our sun is like. A decent amount of mass, but not a ton. And as you can see with this one, we go from a main sequence star, eventually becoming a red dwarf, planetary nebula. This is when the red star has expanded and it's starting to come back on itself, eventually resulting in a white dwarf. If you look at the next one up, you can see the first time that we get to what's known as a massive star. So once again, more matter for the protostar. This blue supergiant results in a red giant star. And you can see as its course of its life, this red giant star eventually becomes a blue giant and then becoming a supernova. The supernova, then this explosion, this massive type of energy results in either a neutron star, these are really small, fast spinning stars, or it can result in a black hole. And you can also see the next one, this more mass, bigger nebula, this blue supergiant, even bigger than the one before, this huge supernova occurs. In this huge supernova, we get to a black hole. Basically the one right below the top one, even more mass, a bigger blue supergiant results in a black hole. And if you look at the very top, these are nebulas with the most energy out of everything. And what happens here is that these become these blue supergiants. You get this massive supernova. And actually after these explosions, what you're left with is you're known as a stellar nursery. And these are actually where new stars are made. One thing we need to always keep in mind is that in our universe, matter is neither created nor destroyed. It just is. So the amount of matter we got at the beginning of the Big Bang is the same amount of matter that we have now. Rather, what happens is that it's simply transformed. So thinking a little bit like if you light a match or a piece of wood on fire, right? the wood burns and it gives off heat and it gives off light, and you see the wood getting smaller and eventually becomes ash, and you think that it's gone. Well, it's not actually gone. All that's actually happened is that the matter that was inside the wood has disappeared in the form of heat and light, but it's simply been transferred to something different. That's the same with stars. Once stars die, they simply transfer their energy into something different. So what we're looking in this slide is we're looking at what is known as a protostar. And protostars are the very birth of stars themselves. And basically, stars can stay as a protostar for hundreds, if not thousands of years. And actually, if you look at this picture here, you can actually see, taken over the course of the month of December, a protostar getting more energy. You see it starts at the very beginning at the left, and by the time you get to the 26th, it's very, very bright. More energy, more heat has come together. This slide talks about the main life sequence of a star. So, and that's actually what our sun is currently in. Our sun is in its main life sequence. Our star is about 4.5 billion years old or so. And it'll burn for about another 4.5 to 5 billion years before eventually it will die out and become a black dwarf. So after a star is born, it's known as the main sequence. And this is the stage where the most energy is given off. And what's happening right now in our star is we're having tremendous amounts of nuclear fusion occurring. Hydrogen atoms are bouncing against each other faster and faster and faster. And as this happens, they give off energy in the form of heat and light, which in turn is what allows for us to actually have life on our planet. So stars come in a couple categories, and what our category is ours is a medium-sized star, but stars come in basically small, medium, and large, going all the way up to extra large, almost like the supersize me concept at McDonald's. So small and medium stars are about 0.4 to 3.4 times the size of our sun. Our sun's a medium star, and it's been in its main life sequence for a long time. Over the course of these stars' life, what they do is they convert hydrogen into helium, and this chemical change is actually what gives us the energy that results in the sun giving off heat and light. Now, hydrogen eventually will get burned out. It's almost like a lighter, right? If you keep the gas flowing, eventually the gas goes out, and so does the flame. So once all of the hydrogen gets depleted, our star begins to turn helium into oxygen. And eventually this oxygen to carbon, and all of these changes eventually result in our star dying out. One thing I want you to look at for this picture, just to give you an idea of scale, is Earth is about 93 million miles away, or 1 astronomical unit. We know this from the last unit that we learned about in terms of distance. But would you actually see this little almost looks like a circle per se, or like a half circle. This is a solar flare. This is just a shot of energy being given off by the sun right now. But I want you to look at this at just the overall size of our planet in comparison to the sun. And it's a good way to get scale and understanding of just how truly massive stars are, especially in our solar system. So massive stars, these are stars that are at least 5 times the size of our sun, and there are many stars that are like this. But what I really want you to pay attention to on this slide specifically are the pictures of star size. So if you look all the way at the left, the red dwarf, very, very small star. You look at our star, on the other hand, a good medium-sized star. If you look at the very bottom, this red giant, these are old stars, and what's actually happened is they've started to shed their outer layer. They've really started to expand, because as the hydrogen gets burned up, as the core starts to lose energy, the gravitational pull becomes a little bit weaker. So the actual star itself starts to expand out. And that's exactly what's happened here in this red giant. It started to expand out. Now, if you look all the way at the top right, you see this blue-white supergiant. And this is a massive star. And these stars, you'll notice, burn blue. And that's because blue has to do with the hottest heat that we can get. So oftentimes people think that red is associated with flame and fire. That's really hot. But if you were to light a match, or a fireplace, or even just hold a lighter, look at the source closest to the heat, closest to the gas for a lighter per se. You'll notice that that's blue. And that's because that's the hottest temperature it is. And as the flame gets a little bit farther up, a little bit higher, a little bit farther away from the heat source, it turns red and orange and yellow. And that's actually why you can hold your hand a distance away. And now you don't want to hold it to the point where you're going to burn yourself. But you can still hold your hand a distance up. You can feel the heat of the flame without actually burning yourself. But a good reminder is that blue is the hottest, and red becomes weaker. So these red giants, these are formed when stars actually begin to die. And what happens is the outer shells start to expand. So the inner temperature decreases, there's less hydrogen, there's less energy being produced by the star, and as that happens, the star itself starts to actually expand out. This becomes what's known as the red giant phase. Red giants can be up to 100 times larger than the main sequence star, and this is how planets actually can get destroyed in solar systems is as stars reach the red giant phase, as they start to expand, they simply consume all objects that are in their path. So eventually the Earth itself will get consumed by our star is as the star reaches red giant stage, as it expands out, eventually that'll actually come and it'll consume our planet itself. One thing to keep in mind is that all stars do reach this red giant point. It's just a question of whether or not they become a super red giant or just a typical red giant. One thing to look at really quick, especially for this picture, is this is just a comparison. You can see our sun all the way to the left. You can see a small red giant expanding out, and you can see a larger red giant that's expanded all the way out. And that's just to give you an idea of how truly massive a red giant can be. As you can see, it's significantly larger than our star. And just imagine what would happen to any objects that are in its path is it just gets hit by a wall of flame. So just like every other object in our solar system, our stars also will die. So as a star begins to run out of hydrogen, its outer shell expands. This is the red giant stage. While the inner portion of the star actually collapses in on itself. It actually starts to stabilize. One thing to remember about nuclear fusion is it's extremely unstable. It's tons of really rapid, fast motion. And that's what produces the energy. As a star starts to stabilize, on the other hand, it actually produces less energy because there's less smashing of atoms together. So what happens at the core of our star is the helium starts to bind together to create carbon. This carbon eventually stabilizes more, and once the core in the center stabilizes, the star actually dies. And once this happens, an outer layer, kind of like a cloud, forms. This is called a planetary nebula. So if you look at this picture down here at the bottom, what you're seeing is a planetary nebula. You notice that the middle is blue, still the hottest portion, but the farther you get out, the lighter the color gets as it gets weaker. But this is also the example of the dust that is currently being formed as a planetary nebula is coming about as a result of a star starting to die. So massive stars will die as well, but when a star dies, its outer layer has only about 20% of its initial mass. So eventually the carbon core collapses, and this is what is known as a white dwarf. These white dwarfs give off very little light, and this light is white, hence why it's called a white dwarf. And once they run out of energy, they become black dwarfs, which give off basically no light. And what you can see with this picture down here in the corner is a really good example of what components make up a star, where the energy is held, where the hottest portion is at the center, and how a star reacts as it starts to die. So massive stars die as well, and these massive stars die in very extraordinary fashions. So once a massive star reaches its red giant phase, the core temperature can increase to over 100 billion degrees. That's a number that's just beyond comprehension in most cases. And once this happens, it starts to actually absorb energy. The center starts to absorb energy, kind of like a sponge, sucking in everything. And it's sucking everything in because it's trying really, really hard to keep itself alive and going. As it sucks energy in, though, it gets tighter and tighter and tighter, and eventually it kind of explodes. And this explosion is what's known as a supernova. These supernovas are massive explosions that just destroy everything in their path. But what they do is they create new debris to create new stars, moons, or planets. And once again, a reminder, mass in our and materials in our universe, they aren't created or destroyed. Rather, they just change shape. So a good way to think about this would be if you had a balloon and you filled it with confetti. And if you were to blow this balloon up, 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 and eventually it pops, what happens? The confetti goes everywhere. Now, imagine if this confetti were everywhere and this confetti were actually to start to spin, to come back together, this confetti being the leftover remnants of the supernova. And as this confetti came back together, it actually started to form a bunch of small balloons. And eventually these small balloons would form and become new stars or planets or moons. So this picture right here, what you're looking at is you're actually looking at a supernova occurring. You can see this massive explosion of energy, but you'll notice that these supernovas look a lot like nebulas. That's because supernovas are giving off new material which will be used to form new nebulas, new gas clouds made up of hydrogen gas and dust particles. Sometimes, though, these supernovas result in what's known as a neutron star, and these neutron stars are really fast, really dense spinning stars, and what they do is they give off bursts of radio waves. These radio waves are what are known as pulsars, and you can actually see in the picture down below, these are very timed, just basically shots of radio waves coming out. These pulsars, scientists can track and they can see, you can actually almost hear them at times. Since they are radio waves, you can actually pick them up with the right type of device. So finally, to the point of the lecture that everyone's really excited for, the formation of the black hole itself. So black holes are the remnant of massive supernovas. Basically what happens is a carbon core contracts on itself, creating a black hole. Think about it like this. Let's say you had a balloon that you'd blown all the way up and you had covered with tinfoil. Imagine if you were to pop that balloon, and at the same time you pop the balloon, you were to crush that tinfoil together, forming a really tight ball. That's kind of what happens with a supernova when a black hole is formed. Basically, everything rushes out, and then it just crashes right back in on itself, creating a super strong pull. In fact, it's the strongest pull in our known universe. And black holes are so powerful, they're so strong, and they're so dense that nothing can escape its gravity, not even light. And now we know that light travels extremely fast, so that gives you an idea of how much power a black hole has in terms of holding its material in. One of the really interesting things about black holes is because nothing escapes it, including light, you actually can't see them. So actually what scientists know about black holes is what they'll actually do is they can actually look out into space, they can take pictures, and then what they'll see is kind of like a spiral motion going towards the center for something. Think about draining a tub. Right? You go to drain a tub, all the material gets sucked into the middle, and it doesn't matter how far away the water is. Eventually, the suction or the gravity all pulls it into this one central place in the tub, which is the drain. It's a lot like the supernova. Everything eventually just gets pulled into this center. And what scientists actually see is they'll actually see light spinning in a circle, spinning in a circle, spinning in a circle, and then they'll see this black, empty middle. And that's how they know that the black hole is there. And actually what happens is eventually this light disappears. Now, one of the most fascinating things about this, though, is that because nothing can escape a black hole's gravity, or at least nothing we know of, we don't know what happens inside, or we don't know where they go. I mean, a hole in space, in essence, would go somewhere, and the question would be where. And that's one of the great questions of our time is what exactly do black holes do, and how do they work in terms of the energy that gets pulled inside of them? So what you're looking at in this picture is this is a theoretical concept of what a black hole looks like. You can see energy swirling around and towards the middle, and what you can see is you see the actual middle itself. And now this is an actual black hole. It was discovered by a NASA telescope. You can see as you get towards the middle, things are getting pulled further and further in, and eventually what actually happens is that the energy gets sucked in the middle, and it disappears. And the question then obviously becomes, where does it go? This now concludes the PowerPoint lecture for the life cycle of a star. As a reminder, it will be posted on Edmodo. I encourage you to look at it throughout the unit for help. It's a good way to get information and content throughout. Also, I encourage you, once again, I know Twitter is new to the classroom, but I do encourage you to follow me at Mr. BG Science. Please have your family follow me as well. It's great for your parents to see. And if you have any questions, please feel free. You can tweet them to me. You can put them on Edmodo, or you can just come and talk to me in class. I hope you enjoyed it. Have a good day.